FooPol, intelligent tools for policy design.
Welcome to another FooPol podcast. This time we'll talk about how we developed the FooPol core platform. It's all about software engineering here, so we guess that some of you might find this boring. Those of you that are interested in stuff like agile development, continuous integration and test automation should continue though. Developing software in a research project has its challenges. Above all, the product scope is far from being set in an early stage. In fact, it changes frequently as the scientific staff produces research results. Our pilot cities start using the software now, and as they do, they learn about social media usage in their context. Usually this generates many new feature requests. Software must deliver value at the end of the rollout, and it's very hard to anticipate what that might be in the early stages. What's true for a larger commercial project is even more true in research development. Quality is defined as the degree to which the user expectations are met. Unfortunately, these are assessed at the day of delivery. So there is no point in following a plan that has been set at the time when the project started. This donkey-like behavior would automatically lead to software of bad quality that fails in delivering value to our pilot cities. Instead of that, a more agile approach has to be taken. We have to accept that there is a somehow stable vision that we can focus on, but that the product scope will change frequently. Development has to follow demand in a flexible way. That's why we've chosen to use Scrum as our software development process. Scrum is a well-known agile management approach suitable for research projects. It tries to optimize the delivered business value while at the same time supporting high productivity and frequent scope changes. Scrum introduces the role of the product owner who is in charge of the product scope. He is the one that maintains the product backlog that, at any given point of time, describes the whole product on a level that is most appropriate by that time. Most appropriate means that only those functionalities that are likely to be implemented soon are defined in detail. Features that are far away in time are left on a rather vague level of definition, because it's likely that they will be changed until we have a chance to implement them. This way, the team prevents situations of planning things whose plan will never be used, reducing waste. The product owner describes features as user stories, a very lightweight form of description. In fact, a user story is just a sentence describing who wants the feature, what the feature is about and, very important, what the requester wants to achieve with it. All these stories are put into the backlog and are sorted by their priority. Priority is just the equivalent of the business value, or how important this feature is at the current point of time. As the project continues, the backlog will change frequently. New stories will be added upon request from our research partners or by the pilot cities themselves, while stories that are not required anymore are dropped from the backlog. This allows the team to follow the demand in a flexible way and finally delivering a product that best fits the customer's demand at the time of delivery. Doing agile development requires some core tools and working procedures. Without these, the team just couldn't follow the frequent scope changes and would build up technical debt, a burden that has brought down so many larger projects. In the next few slides, we're going to present you some aspects of our working process and the tools that we use. The whole system is built around feedback loops. Everything that we do will trigger a tool whose purpose is to provide feedback to those team members that applied the change to the product. The first feedback loop is quite common. The developer's IDE, we use Eclipse, generates feedback upon compilation. If anything breaks on a syntactic level, the compiler will likely find it. Of course, except for some reflection-based stuff for the experts. This feedback is very fast. Seconds after anything breaks, there is the warning signal. The second feedback loop is the continuous integration server's unit and unit integration tests. Every time a developer checks in code, the continuous integration server grabs it from the source code repository and triggers a full project build in a clean and defined remote environment. After that, the unit test suite is executed. These tests cover basic stuff like functional tests of single methods, classes or modules. If anything fails, then the developer will get feedback by email within a minute. Jenkins, an open source continuous integration server, is used to manage the CI process. Cobertura is used to assess the test's coverage by instrumenting the product's code and tracking each touched statement. This way it's possible to calculate the rate between tested and untested code, providing the test coverage percentage and important test quality metrics. The third feedback loop involves the functional regression tests. These are fully automated black box tests that simulate the user's interaction with the core platform using a script-based automated test suite. Selenium is used for that purpose. Execution of these tests currently takes about 10 minutes, but it's likely to increase to 30 minutes over the project's duration. Again, in case of an error, the developer will receive an email and Cobertura is used to assess the code quality. The fourth feedback loop involves a white box test of the whole source code base. Every file of source code undergoes a syntactical, coding style and problem detection stage. Sonar Server is used to execute these tests. The coding style and possible errors are detected using checkstyle. The fifth feedback loop is the manual tests that are done by the team's testers. There are still some tests that can't be automated in an economic way. Usually this involves very rich parts of the user interface or non-functional requirements as usability. So, after every development iteration, there are still some tests that must be performed by a human tester. Manual testing is expensive, prone to error, and it takes its time. So we try to keep the test automation rate at a high level, but as I said, there are still some aspects that can't be automated. In the worst case, the developer will get feedback at the end of the current sprint, which is almost every 2 weeks. The final and most important feedback comes from the actual users of the software. They might not be educated and certified testers, but they have valuable real-life domain knowledge. In other words, our pilot cities will focus on testing if the features fulfill their purpose and are valuable for their municipality's business. While the technical stuff most likely focuses on testing if the team implemented the things in the right way, the pilot cities will test if the team did the right things. In order to get frequent feedback, we had to find a balance between early delivery and testing effort by the municipalities. So we decided to deliver every 2 iterations, which is once per month, to the demo platform. The demo platform is the final stage before production. It hosts the release candidates before they are rolled out. This podcast covered some aspects of the software engineering parts of Fupol. We tried to show you how the team handles the frequent scope changes that are so typical in a research project. Preventing the build-up of technical debt, automating tests, and implementing multi-stage feedback loops are key to success in such an environment.